raise your hand if you're familiar with SWE-Bench or like that style of coding benchmark out there. Okay, I'm going to approximate that as everyone in the room, but I will just give a quick note on how these generally work. Kind of two types of, or a dichotomy I would point out in terms of a number of especially coding benchmarks are tasks that are based on work found out in the real world and tasks that are constructed fresh. So, our friends at Terminal Bench, a fantastic benchmark, that is an example of tasks that are constructed fresh, where I'm coming up with an idea for, a terminal task that's a challenge to a recent agent. On the other hand, something like SWE-Bench and Senior SWE-Bench are based on work observed out in the real world that people have already done. So in particular, looking at PRs on GitHub that reflect real work that people have put into production repos out on the web. Originally, SWE-Bench could have been any PR out in the world. So this could be, adding a small test or changing a helper function. We do a lot more kind of careful design and discovery as part of Senior SWE-Bench to find PRs that are reflective of, again, longer horizon, more senior or tasks that require a combination of different senior engineering skills to complete successfully. So a few different things that we do. One, as far as repos, we go and look for multi-service applications, tools, and libraries, production grade ones, and actually mostly ones that started after 2020, because these tend to have much higher velocity of changes, new features, and major bugs getting fixed in them. The PRs that we actually go source are from February 2026 and after, which is after the knowledge cutoff for most of the most recent models. We also group multiple PRs into single tasks to expand the scope of work being done. So you could imagine that someone is creating a feature in a repo and they do it over the course of like 5 PRs. We go back and look at those and kind of merge the scope of all of those changes into a single task. And we look for PRs from authors who we know to be repo maintainers or people who have hundreds of commits into the repo. This lets us trust the quality of work being done as something that required the most experienced folks. And also what we use as the reference solution, the code that these folks contributed directly, we can trust it as decisions being made by the real experts in the repo. Within Senior SWE-Bench, there are 2 primary task types. The first, which again represent the kind of work that we see a lot of senior engineers doing. The first are investigate and fix tasks. So these are bug and performance fixes that are typically represented like a bug report on Slack. And the second is a design and build, which generally looks like complex multi-component features and migrations, where we give a general scope like a message from a PM or a tech lead of what we want to build, the behavior that we want it to have, but not any of the specific technical details. We'll take a closer look. And then just a small sampling of some of the repos. It might be a little bit hard to read, but just as a quick scan here. Again, all of this is available on seniorswebench.snorkel.ai, so you can go look in more depth. But things like PostHog, a production analytics platform built in Python and TypeScript, to Electric, which is a Postgres sync engine that written in Elixir and kind of much lower level data engine code. Okay, cool. So I think one of the best ways to understand Senior SWE-Bench is to look at a specific task. So I'm going to do a classic talk momentum killer and play a video. I promise this will be relatively short, but what this is Gabe, who's a Senior SWE-Bench contributor, talking a little bit about the source of one of the tasks in Senior SWE-Bench. So I'll get into this in a little bit more depth. At the risk of being too meta, the PR that he's talking about, the feature that he's talking about, was made into the Harbor framework itself, which is a common framework for running evaluations. This is something I notice across all different kinds of benchmarks, which is that AI people tend to pick repos that they know and they use because they couldn't possibly imagine, a full stack application other than MLflow or something like that. There's nothing special about this. There's nothing special about the PR being made into Harbor itself. But another quick raise of hands, who here is familiar with Harbor? Okay, well, I'm going to again approximate that as everyone in the room. So I think at least people here will have a little bit more context potentially for the change that he's making. What he's describing is a change that he made into Harbor to allow multi-step tasks. So these are typically tasks have an instruction at the start, then the agent works, and then you run a verifier at the end. What Gabe wanted to add was the ability to run a task with an instruction and a verifier, and then run another step and maybe another step, each of which have their own instruction and verifiers, and you get something out at the end after the agent has gone through multiple steps. So he's just going to talk a little bit about the design process for this feature.
A little bit about the approach to design that you took with Alex, the maintainer of Harbor.
Yeah, so there are really countless ways that you can go about adding in multi-step trials, right? You can do it in the original way that we thought of, which is have a bunch of isolated environments. You could do it by adding in a way to link trials to each other so that it's essentially a DAG. You can do a lot of different things, but the one we settled on was just adding something to the config that says, here are the steps to run, here are where they are, here is where they are saving to. And the reason we went with this is, one, it's really simple, but also it kept the existing trials portable. And it preserved all the existing semantics that Harbor had in place, so no trials would be broken. Right? If you were to download, a SWE-Bench trial from Harbor, it would not be broken if you're using this new version. And so those were the core constraints that we wanted to operate on, and this solution fit that perfectly.
Awesome. Makes a ton of sense. And then how about implementation? Tell me about a couple of the trickier or more nuanced things that you came across as you actually got to implementation here.
Yeah, besides the avoiding any degree of regression, what we really realized is that we need a way to aggregate the rewards in a smart way, right? We have every single step has its own reward, and we wanted a way to give people the flexibility to either average those or just take the final one. And the issue with averaging is, if one step is missing a key, what do you do? And I think the most obvious thing that we landed on is that it should be counted as a full failure and a zero. The other big thing is that every single step could have its own setup, right? Like, you may add new conditions to the environment. It's not something that I would have realized, but every single setup needs a health check, right? Existing trials had health checks. And so thankfully, Alex caught this, and he realized this, as we were reviewing the PR. And so he added in a health check that would check, has the setup done its job, right? If that setup has not done its job, fail immediately. It's just something that you don't really think about until you've ran into an issue where setup is silently failing and you're trying to debug a very expensive run.
Awesome. All right. Thanks, Gabe.
Okay, cool. So I saw a lot of people out there, focusing on their bubble tea or Kalshi or whatever they're doing at, 4:45 these days. If your eyes glazed over during that, that's all good. Basically, Gabe was kind of describing that there is a pretty wide design space for this and a lot of different tricky elements of the implementation that you can go right or you could go wrong. And what we want to do is challenge agents to navigate that full design and implementation space without us having to guide it along every single step of the way. Because again, I'm sure everyone here can relate. That's how everyone here uses coding agents, right? You just give it something that you want. You maybe give it a couple of pointers and you expect it to do the work correctly and right. See a question in the back? We're going to do questions like in 4 slides or something like that. So just hold on there and we'll get a chance for a couple others. Okay, cool. So let's look at, so we looked at Gabe's really great work into Harbor here, and we turned it into a Senior SWE-Bench task. Let's look at what the instruction for that task looks like, which is what we give the agent before asking it to go out and solve it. So this is what it looks like. This looks very, very different than the highly specified, basically full technical specs that we saw in comparison earlier in the presentation for previous generation coding benchmarks like SWE-Bench Pro. Here we are basically giving it some high-level context about what we want achieved, a few different kind of design notes, and then some descriptions of the behavior that we want, like user stories. Which is something, again, reasonable that a PM might send to a senior engineer on Slack. Again, very, very different from the highly spec'd out technical thing that we saw before. Now, like Gabe was talking about, there's a very wide design space of choices that an agent might make. It could go this way, it could go that way. We want to make sure that it's able to choose the correct design for this feature, or a near optimal design, and implement it correctly without making a bad choice. Now, The takeaway at the bottom. So most benchmarks, the reason that most benchmarks use those super overspecified, basically full text specs as instructions is to facilitate pre-written verifiers. So the way that you assess whether the agent did something right or wrong is I write a little, basically like a unit test beforehand that checks whether all the conditions have been met. And you can really only do that if you kind of know the interface and the exact behavior that you're testing against, which is, again, why those instructions are typically written out in such detail. But we achieve in Senior SWE-Bench reliable evaluation with highly realistic instructions like this, which I'll go into in a little bit. To make this a little bit more grounded, maybe I can zoom in here super quickly. We're now looking at the actual code that Gabe wrote to implement this feature when he did so originally. Let me just give one example. So as part of this, he chose to basically Harbor will recognize that the task has multiple steps if there is a directory called steps. He could have very easily named this phases or task_steps or anything else like that. That is an implementation choice that was totally up to Gabe, as are many, many, many other choices in this patch. If instead we had provided a full technical spec as instructions, there are basically like no choices for the agent to make when it comes to implementation and few when it comes to design as well. And so by creating, highly realistic underspecified instructions, we widen the design space that we expect the agent to navigate significantly and create more challenging, longer trajectory tasks. Now, the key here is how we achieve reliable evaluation like we would have with pre-written verifiers. And that's basically what I'm going to talk about next. Okay, so how we achieve realistic instructions with reliable evaluation in Senior SWE-Bench. So the first one is testing behavior, not implementation details. Many of that kind of previous generation of benchmarks basically tested, little helper functions and small choices that were made. We don't do any of that. We just test behavior through system interfaces like APIs, CLIs, front-end components, service interfaces. We basically raise the interface that we end up testing against. And this helps us test directly whether the high level behavior that we specified in the instruction, if this contract has been met. Now, we are certainly not the only people to have recognized this. A number of many concurrently developed benchmarks in first half of 2026 that have come out basically use this first one as a primary impetus. We layer on a couple more things. So the second is a highly principled framework for what can be tested fairly, right? So not everything is laid out in the instruction, which opens up the question of what are we allowed to test without it kind of being an unfair gotcha for the agent of, oh, hey, you didn't name that directory steps. If I test that it was named steps, you could have, again, stages would have been totally fine. It'd be unfair for me to test whether it was called steps or something different. So first, it's okay to test things that are in the behavioral contract laid out in the instruction. That's pretty obvious. We told it, what we want at the end of the day. We can test that that's the case. Second, are looking for, load bearing. Unfortunately, I came up with this word before, I forget which model started spitting out this term as like a, classic AI slop thing, but so I'm going to leave it. I use M dashes still. I'm still a human. I'm going to use load bearing in this case, but load bearing code base practices. So these are looking in the code base for consistent patterns that impact functionality, where if you didn't use that same pattern when making a change in the code base, a senior engineer would probably reject your PR, right? I would reject something like that quite often. If you invented, for example, your own auth framework for a new API endpoint, rather than using the existing one. So that is a fair thing to check as well. The last is a general best practice. So something that would be obvious to a senior engineer, even if it's not exactly spelled out in the code base, but there are no defensible alternatives. So imagine an API endpoint that lists out a bunch of items in the system. If that number of items could grow to like 20 million and you don't cap or paginate that API endpoint, that would be completely unacceptable to a senior engineer, no defensible alternative. And so something like that is fair to test as well. Basically, everything else is testing implementation or random choices and is generally not fair to test. The last thing I'll call out is the adaptive runtime verification with the validation agent. We're going to go into detail on this, one of the main technical contributions of Senior SWE-Bench. But the idea is that rather than just relying on pre-written verifiers, we also have an agent that can write verifier tests adapted to the specific code that the agents have written to solve the task, so that we don't need to spell out all of the interface and behavioral details in the instruction itself. We can actually adapt to whatever choices the agent made afterwards. So more on this next. Okay, this is the overall map of what a Senior SWE-Bench task looks like. Again, this will look familiar-ish to people who are familiar with Harbor or familiar with SWE-Bench itself. The first phase is the agent trying to solve the task. So it gets an instruction, it runs, and it produces a code patch as a solution. That code patch then goes into the reward phase. And this is where Senior SWE-Bench is a bit different, where we have multiple different reward mechanisms running, not just, say, pre-written verifiers. I'll touch on a couple of these and then go into more depth on the other two right afterwards. So the first are pre-written verifiers. So these are expert written tests that look basically like unit tests in whatever language of choice that produce, pass or fail. The second is the validation agent. I'll skip that because we're going to go into more depth in a second. The third is a task-specific rubric assessed by an LLM judge. This is like pre-written verifiers, a pretty standard technique. And then the taste judge, I'll go into more detail on that in a second. Let's skip those other things because we're a little bit short on time. Okay, so let's talk a little bit more about the validation agent in depth. The two main mechanisms that people use to assign rewards for benchmarks like this are pre-written verifiers. So again, unit tests that something must be true if the task was solved correctly. And then LLM judges, where you give like a rubric or a prompt to an LLM. It goes and reads the code and says, yes, this was met, or no, this was not met. So pre-written verifiers are great because they actually run the code. They're deterministic, and I know what I'm going to, if written well, and I know what I'm going to get out of them. The trade-off is that you have to do those like unrealistically spec'd out instructions to avoid false negatives, especially for tasks where the solution involves changing the interface. LLM judges are, an advantage that they have are that they can adapt to different shapes of the solution. An LLM just goes and reads the solution and says, did this, in whatever way it chose, did it meet this condition? But the problem is that they don't actually run the code, right? So something might look plausible, but it doesn't actually even compile or something like that. So they're far less reliable, but they can adapt. Our goal was to come up with something that gets the best of both worlds, where we can run the solution code, but adapt to specific choices made in the solution itself so that we don't have to spec out everything in the instruction ahead of time. So that's exactly what the validation agent does. I'll go into a bit more detail about how that works right here. So the validation agent works in basically 3 steps. So it is given the agent patch, which is the output here from the solution from the agent. And it's also given this expert designed test spec, basically a bunch of recipes written by one of our expert contributors designing the task, which says how the task should be tested in slightly more abstract terms. The validation agent will then go use the spec and looking at the patch to see what choices the solving agent made, go and write a bunch of different test scripts to implement the validation spec. Those test scripts then get run programmatically with a bunch of different test cases. So parameterized over a bunch of different inputs and outputs, making sure that they all pass. And then there's actually a revision stage where an LLM judge will look at the test scripts that were output and maybe give the validation agent some feedback so it can go revise them and make some tweaks if it missed something. Then we'll do kind of a final run of all of the test scripts. Again, this has no LLM in the loop. It just is running verifier scripts like you would normally. They've just been produced by this validation agent. And then we get some scores out of them, seeing how many cases pass or fail. The validation judge at the end also kind of makes a judgment as to whether we should discard the trial or not. If, for example, it saw that the test scripts were or the validation agent was colluding to help the test pass. This is very rare, but it's important to have a guard like this. A couple other quick notes on how because again, this is introducing a stochastic element or non-deterministic element to this process. And so we want to make sure that we can really rely on the performance of the validation agent, because if we can't, then who knows if these tests passing means anything or not. So a bunch of things that we've done to make it reliable, including closely aligning its system prompt to be a test engineer, running it multiple times on the reference solution to make sure it always passes, in addition to an empty solution to make sure it always fails. We have the LLM judge, the validation judge, that does a check to make sure that it's done all the work that it's supposed to. And then having each test be parameterized multiple times to avoid being able to pass in or hard code certain values in these tests as well. Okay, so let's look at a more specific example for the Harbor task or the task that Gabe built. Again, here's the same instruction that we saw before. There is a pre-written verifier, and we can do this because an important condition of this task was that the stuff that worked before continues to work. So if I do a single step task, that better still work now, and I know exactly how to run that as it does today. So this is basically what that's doing, and this is a good fit for pre-written verifiers for a feature task like this. We then have the validation spec here, and I'll just, again, it's probably very hard to read, especially for folks in the back, but basically there are 4 main procedures in the validation spec. This one is basically, if I run multiple steps, it runs in order and aggregates the solutions, basically the general gist of the task here. The procedure on the right-hand side, which is expert written beforehand or expert designed with the help of a coding agent, basically tells the agent to look at a bunch of specific things about how the solution went about implementing this, and then use a helper script to go and run it and then check the outputs to make sure that they're correct. Again, it's not spelling things out exactly. The LLM agent will write the script out exactly against the solution that the solving agent produced. But it will run this kind of more deterministic procedure, after adapting in that way. And then we'll run multiple test cases just to make sure that, with different edge cases and other things like that, it's going to work correctly. Okay. The last thing I want to call out is what we call the taste judge, which is basically a way to score not just correctness of the solution, but code quality, and do this scalably so we don't have to have highly customized code quality assets or rubrics for every single task that we produce. The idea is to create a technology and practice agnostic rubric that assesses the quality of the code relative to the code-based practices and the reference solution itself. I've included the rubric here below, which give a sense of, these are summaries, of course, of the rubric. They're much more in-depth. But just to motivate this, let me give an example of something like documentation. So if I were just to write an LLM judge that we're trying to assess, did the agent do a good job at adding documentation? I might have to wire something in, a personal belief that you should always have documentation that says input parameters and output parameters and all this kind of stuff. Well, many code bases don't do that, right? Many code bases make a specific decision to forego highly detailed documentation to move faster or whatever. I was at Facebook during move fast, break things times. That was very common practice. What the taste judge does, it doesn't apply any of those kind of judgy or preferential things. It just looks at the code base for the actual practices around the code that's being submitted and says, basically, does this code fit in with all of that? Does it observe those same practices, whatever is there today? So again, this is something that can scale to any code base, any technology, without being overfit or too judgmental. I'll also note that the taste judge, we don't just take the raw output scores, we apply a very conservative threshold, basically making sure that it did better on an A to F grade scale, did better than a D. And if it's not really bad, then it passes this threshold. Spoiler alert, a lot of solutions do not pass this threshold, which is very interesting to me. Okay, lastly, I'll just quickly note, very, very extensive quality control process in building tasks for Senior SWE-Bench, both a lot of refinement with automated tooling and then multi-stage expert review, including our research team members looking at every single task. Benchmark is only as good as it is reliable. QC for long horizon tasks takes a lot of work. So anyone out there thinking about building your own benchmarks, prepare to spend a lot of time on quality control, because it's, from my perspective, basically this gates whether the benchmark has any value or not. And of course, no benchmark is perfect. A few different things I'll call out about Senior SWE-Bench: additional expense and execution time, because you have that agent step during the evaluation phase. There are also multiple deterministic elements, basically the same flavor: the validation agent, the taste judge, task-specific rubrics. If you need something to run exactly the same way every single time, then look for another approach. But again, this is a trade-off that we very openly make to be able to have highly realistic task instructions. So from our perspective, everything runs as reliably as you'd need to have this kind of up-leveled evaluation of agents. Okay, great. So I know we're kind of like at time. I have a few more slides. Let me take some, actually, you know what? No, we're gonna do questions at the end because we need to move through this super quickly. Live audible here. Okay, cool. Just quick snapshot of the current Senior SWE-Bench leaderboard. So this is, I was trying to get Thinking Machines new model that they put out today in. Unfortunately, it's not completed yet, but this is still relatively up to date. Fable, just a couple things to call out quickly. Fable 5 leads the pack with 29.1% with our kind of high quality solve metric. It does, however, cost a lot of money. If I switch this over to, is the drop down there? Okay, I'm going to go from Zoom. There we go. Okay, well, whatever. I have this number memorized. What am I talking about? It's $29 per run. So per task, it scores the highest, but it costs $29 for every single rollout. Very interestingly, Grok 4.5, which came out the other day, it is not really super close to the top of the table. It's fifth, but pretty far off from where Fable 5 is. By comparison, though, it costs about $1 on average for the runs. Really interestingly, and let's go to the other slides and take a closer look. So we've mapped out the kind of Pareto frontier of cost versus performance. So like I mentioned, Grok at 17.2, very economical option, about $1 per task compared to $29 for Fable 5, even though it scores significantly higher. I think really interesting comparison with the new GPT 5.6 Sol model that came out. Highly efficient, only like $3 per task, as compared to Opus 4.8, which is about $8, and they score very, very similarly here. By looking at some of the performance of these models, especially on these, again, senior engineering tasks, I think it is really revealing about the trajectories of some of the labs. So you look at plotting out kind of how Anthropic models have progressed. They are achieving by far the highest score. Yeah, they're achieving definitely the highest scores on the benchmark, but at much, much higher token usage, like 290K output tokens on average per task for Fable 5. If you look at the trajectory for OpenAI models, up and to the left, which is really interesting. This means that they are getting both more performant and also more efficient. GPT 5.6 Sol has like a tenth of the output tokens of Fable 5 and scores very, very competitively. I think it's like the third ranked model right now. Cool. Senior SWE-Bench, I encourage folks to go to the website. It has a very fine-grained task taxonomy, so you can dig into the metadata behind tasks. Just as one example, this is filtered down to performance on just tasks that touch both a Python backend and a TypeScript front end. So very reflective of, I think, a lot of like modern engineering stacks that we see out there. GPT 5.6 Sol is actually the leader here, and significantly, you can see kind of improvement, release over release by the different models, but definitely a jump forward from like 30% to 40% for the GPT series. Here's just a quick example of one of these tasks. Again, just to show the level of realism, this is asking to add a new feature into PostHog with both front-end and back-end elements. And then I think another really interesting behavioral discovery that we've made, this has, I think, been reported out elsewhere, but Fable 5, and this is, I think, guidance to, I imagine a lot of folks here are interested in benchmarking, and so it stands as guidance for you all. The new models are showing much higher awareness that they are in benchmarks. So about 3x more often than Opus 4.8, Fable 5 does or says something that implies it knows that it is being benchmarked, which is very interesting and definitely affects its behavior. This tends to correspond with exploring vectors for reward hacking. So most commonly in a coding benchmark, this is like looking on GitHub to see if it can find the original source task that the task came, or the original source code that the task came from, and like copying and pasting it in. We have a bunch of controls in Senior SWE-Bench to prevent this. Limiting internet access is a common one, but there are ways around that. We don't let it go on GitHub, but it can install packages from PyPy or other package registries, and so might go try to find the package for the repo that it's working on, install that, unzip it, look for the code in there, and like copy and paste it. So lots of different things that you need to look out for. These models are very smart. They are trying to accomplish these tasks, achieve the reward and do it efficiently, but that can lead to unexpected behavior. And so highly recommend anyone working on benchmarks do close analysis, read trajectories to see what's going on, and be aware of things like this. Okay, and that is it. We're at the end. I'll just leave the leaderboard and overall design of Senior SWE-Bench here. I know we ran a little bit long. Thank you all so much for coming and sitting through this. I encourage you all to go check out the website, and yeah, excited to talk to a lot of you. I know a few folks have a bunch of different ideas for benchmarking. Would love to get more in the weeds there. Cool. All right, thanks again. Okay, we had a first hand up in the back, so let's go there for yeah, impossible job for you, but we'll send the mic over there, and then we can get a couple more.
Sorry, two quick questions. What was the website that you published this again?
Yeah, this is you know, I really probably should have put the URL up here, but you're doing your job, or doing my job for me. Okay, here okay, it is Nope, not even that. Senior-SWE-Bench.snorkel.ai. Absolutely wild that I did not put this up. So let me, here, actually, I have a place I can type. One sec. Okay, there we go. Can folks see that relatively well?
Thank you. And one serious question.
Yep.
Most surprising thing that you discovered with this benchmark?
So I do think the benchmark awareness behavior that I pointed out in the last slide was not something that I expected to see. This was kind of like late breaking stuff as we were first publishing the benchmark. Interestingly, the first model that we benchmarked that showed much higher awareness just based on the release timeline was Sonnet 5. I think as you know, that just seeing the behavioral similarity between Sonnet 5 and Fable 5 versus Sonnet 5 and Opus 4.8 on this kind of specific aspect, I think is really revealing in terms of like how those models are related to each other. So this was something that happened relatively recently, but I think was definitely something that we didn't fully expect to see. I'll just quickly note, a lot of benchmarks out there make assumptions based on oh boy. Okay, based on this kind of previous generation behavior where reward hacking was relatively uncommon. And so people, while there was exploitable topology, like you can go look something up on GitHub, it was in practice inert because models just weren't actually attempting to do that. If people are just running new models without checking for this kind of stuff and putting in safeguards for, getting around or achieving the task in a way that is not really the full intent, there could be a lot of misleading results out there, I would say. Cool. Yes.
So I have multiple questions. First of all, which harness did you use for the different models? Because that makes also like a huge difference, especially when you think about that. What I personally believe is the future, that you basically customize the harness to your code base with like post and pre-tool use hooks and all that kind of stuff. So that obviously changes performance a lot depending on all models. And the other question, how do you prevent like leaky benchmarks? Because like this is the other thing, like basically all benchmarks, you see small models achieving 100%, but they are basically trained to benchmark these benchmarks. And yeah.
Yep, great. Two great questions. So first, huge. Just based on what you said, I'm going to disappoint you massively with respect to the harness. So we used Mini SWE agent as the universal harness because we decided we wanted to basically benchmark the performance of models versus model plus harness combos. Spoiler alert, I think the next generation of benchmarks probably actually going to leap over that combination into something a little bit more holistic. I have thoughts about that. But we use Mini SWE agent to basically put them all on the same level. I will note that we did experimentation with specifically Opus and Claude Code plus GPT 5.5 and Codex. They were a bit better, but not so much better that we felt it was worth reporting out for this. So I think this is definitely like an improvement for the future. But I'll just quickly note what you mentioned about like repo specification, repo customization of the harness. We didn't do any of that. So I think that's definitely like an area of improvement. Definitely requires doing this at scale, requires making sure that you can reliably find that kind of tooling and use it correctly in an unfamiliar repo. The second question that you had about leaky benchmarks, it's a great point. I mentioned our friends at Terminal Bench. They discovered that basically people had packaged goal trajectories into a model distro, and then we're basically just like unpacking them and following them step by step. Super not cool. The main defense that we have against this is a private set. So there are 100 tasks in the benchmark, 50 are public that people can go look at, 50 are private. If we see very significant deviation between the scores on the public set versus they are chosen to where the current models scored very similarly between them. If we see significant deviation, probably means that folks are doing something a bit odd.
Had a question for you about the range of success or failure rate. So you showed the sort of Python backend example, but could you show more of the full scale or talk to what the range of success rates were?
Range kind of sliced across like other metadata or what?
Other task types.
Other task types, sure. Okay, quick plug to go look at the site. Let's see. The taxonomy, the task taxonomy is kind of fully built in and explorable here. So I'm on the tasks page here. If I go to filters on the top right, I can then go filter tasks specifically by stuff that I'm interested in. So maybe I write Go, and so I want to know what model is best for these. And then I can also go look at the agents page and do something similar. So let's say I do a lot of work in Elixir and Go. Looks like Claude Fable, the Claude models do best here, followed by GPT 5.6 Sol. So encourage folks to go here, take a look at these, and you can kind of customize the view to what you're interested in.
Did I see correctly on the previous page that there are a number of different examples where models are getting 0% of tasks right?
On which, tasks. Here.
Yeah.
Yes. So there are a number. So here I can kind of sort the tasks by solve rates. And so about like 50% of the tasks for high code quality solve, it's at 0. Most of them have at least one agent that is passing the basic behavioral checks, so they're able to make significant progress. I'll note one other thing, because I think task solvability is like an interesting topic. Like, are these, especially as people are looking a lot more closely at SWE-Bench Verified and SWE-Bench Pro, finding basically unsolvable tasks. This was something that we wanted to make sure was not the case here. You can look, there are more details on this in the blog post that goes over a lot of the different things that I talked about. One quick thing I'll mention is that we have what's called a guided variant of each task, basically as a diagnostic, where we stick in a bunch of additional guidance about how to solve the task, not exactly, the solution, but how to solve the task, and then how the agents go from that. And all but like 5 tasks were solved with that, just as a diagnostic of, with sufficient, knowledge and intuition, can they go about and solve the task correctly?
Thank you.
Yep.
Hi, thank you for the talk. Did you evaluate the code only as an output, or did you also evaluate the thinking process, like inference process in the middle?
Yeah, so we do analysis on the the full traces. I'll just show quickly, this is another blog post that we have up here, some interesting analysis that we've done about kind of where models are getting things right and getting things wrong. This is probably the most informative thing. We basically broke down the solving process into comprehending, investigating, designing, implementing, and then verifying, and then looked at where different models were doing well versus not. I think, a couple of things that were super interesting to me is like some of the more recent models like Claude, like Opus 4.8, does very, very well at comprehending as compared to many of the other models. And we saw additional advancement here with Fable 5 as well. It's not in this chart, but lets you at least kind of break down over phases, where models are getting things right and wrong.
One more question.
Sure.
What was the most recent model from the open-weighted model that you evaluated?
From open weights? Yeah, so again, tried to get the thinking machines one in today. I think GLM 5.2 is the most. Is there another one? Is there one that you have in mind that is more recent?
Yeah, Kimi and Quen.
I think GLM 5.2 is more recent. So we have Kimi 2.6. We're running 2.7 now. But I know there's a ton of interest in open weights. We're currently running Minimax. We're currently running Kimi 2.7. And then the thinking machines one as well. So we should have more open weight models on here soon. All right. Oh, we got a bunch of football players out here. Go for it.
So I had two questions. So you mentioned that quality control was, one of the biggest challenges. Can you talk about some specifics, like what were, the top few issues? And then the second question is, beyond quality control, what were the top challenges? Like, was it task collection, environment setup, funding for this, anything else?
Yep. I think really, really great question overall. So I guess I'll answer the second part first. The vast majority of our effort went into creating a highly reliable validation agent process. We had a bunch of initial attempts where, based on our experience with coding agents doing really well, we were just like, okay, let's just prompt them once, YOLO, they'll probably write the test correctly. Not remotely the case at all. They messed up left and right. And so we really had to hone in the process of first kind of what expert provided info do they get via the validation spec, and what key pointers or information was most important to provide there, the revision process, and then this kind of handoff between the LLM piece and the programmatic execution piece. So this is where the vast majority of R&D went in, and was far more than we expected it to be. But again, all 100% worth it to have a really reliable, adaptive process for task verification. On the QC, again, another one of my favorite things, asked me to put up the website for the thing that I did, which I obviously should have done before, and then telling me to go back to a slide that I had to skip because of time. So a couple of quick things that I'll call out. So these couple of things, like highly tuned LLM-based checks, running the tasks multiple times multiple times to make sure that they are scoring the same way every single time. The biggest kind of challenge that we discovered early on, I would call out as this one. So the thing that you want to make sure is that the tests or the verifiers in the validation process do not allow for materially worse solutions to pass. So those are false positives, or materially near optimal solutions to fail. So that might be where you're testing something way too specific, where like it's totally fine if an agent made one choice or another. There are a bunch of different ways, especially these false negative risks, that they can kind of worm their way into a task, right? You might write a helper function to exercise the code that an agent writes, and it makes an assumption about like what an API route is called, or what the shape of a payload is. And so being really vigilant and having a very specific process to check for those types of things ended up being super, super important. And again, this was combined both with these types of procedures where we're, again, running multiple reference solutions to look at different ways that these risks might pop up based on different code that could be produced. And then, of course, combine that with our expert multi-stage review, both our research team members, SWE experts from Snorkel AI's expert network, and then also calibrating some of the LLM judge elements as well.
Hi, sticking with the evaluation side, two questions. One is, what is the human, like your expert reference, what score do they get? Second is, how much does it cost each time you run this? And the last question is, what model are you using for the LLM side of things, especially for like the taste side? And do you see any issues with, I know model families prefer their own answers. So like GPT will prefer GPT answers. So what model are you using, and is that a problem?
Cool, all great questions. Okay, so the first one, how do the reference solutions do? Those, we reject tasks if the Oracle patch that we have does not get 100%. So those always have to pass, like no questions asked for every single task, or else it's invalid. The second question, models that we use for, sorry? Cost per run, yes. You can look at that a little bit more closely on like the overview page if you want. But for example, like I mentioned, there are material cost differences. This is just output token cost. If I go down here for total token cost, like Grok down at $1.23, Fable out at 29.37.
Sorry, it's about the evaluation side. So when you do the evaluations, you guys use LLM models.
Oh, great question. Okay, and good thing I have an answer to this. So yes, this is one of the kind of primary trade-offs that I mentioned on that slide about no benchmark being perfect. So we wanted to make sure that both the execution time and the cost itself, there we go, were not like huge deterrents from using the process here. There we go. Okay, so this has actually gotten better since then, but we use as default, we use Sonnet 4.6 as the model for the validation agent. This one really had no like you mentioned, like bias towards same provider, because just like writing tests, right? So, and of course we measured this as well, but the wall clock time overhead was like 6 to 20% median of 11%. And the 20% is really just for ones where like a very powerful model can one-shot something. It's usually, on the lower end. So in a given rollout, like generally around 10% of the time will be taken by the validation agent. And actually this has gone down recently as well. This is a little bit stale. Token cost overhead, median of 6%. So a 6% tax in terms of cost per rollout. Again, if you're doing this at massive scale, that is material. But the higher end of that, we're generally with the far cheaper model. So that distribution is skewed a little bit. If I'm doing rollouts for like Opus 4.8 or something like that, you're much further at the lower end. Cool. Is anyone like in charge here? I know I a little bit am of the company. Hey, and Cynthia. Okay. How are we doing on time here?
One live question and break out the networking, and one ask every question is what I'm wanting to play.
Cool. Okay. Last question. So I see all the tasks are mostly focused on infra and dev tools only. Is there a reason we didn't pick other domains like say finance, repos, or healthcare rep?
Yeah, I see what you're saying. Like mostly software
Yes.
tools. I would say it's not infra and like dev tooling. We do have some dev tools like Turbo Repo and stuff like that, and some other libraries. But I think these are like broader systems, but still, yes, I agree within the software engineering stack itself. So we do have So first off, I'll note there are ones that are a little bit more domain specific. Image, for example, is like a like open source Google Photos type of thing. Paperless is like a document management service, and these are like full stack applications that people just use as kind of end products. One of the goals that we have, we're planning to do future releases, so like more tasks coming out, and doing more domain specific ones is definitely a focus for us, because I definitely agree. It's one step to work in production full stack repos. It's another step to kind of go further outside of the software domain itself, and do kind of more domain specific coding tasks.
And one more thing, if I missed,
Is there a time limit for each task that you set?
So Harbor, which was designed around Terminal Bench, so yes, they set time limits to make sure that things don't go crazy. Originally, people were interested in like doing, shorter, highly efficient rollouts, and so they would want to set the time limits like 5-10 minutes or something like that. As people have become more interested in coding tasks, you see benchmarks with timeouts of like 6-12 hours, something like that, because I want to see, can this thing churn and actually like get through an entire thing. So basically, honestly, kind of to control our costs as part of this, we set solver timeouts of like 6 hours, and then the verification, so like the full validation agent and LLM judge and all that kind of stuff, those are usually like 10-15 minutes or something like that. But those are much more than is generally necessary. The 6 hour kind of time limit for these tasks, I think, is generally representative of some of the more, or the longer time horizon benchmarks out there today.